This is Catherine Nightingale with Chattanooga State Community College, and this is for Calculus 3 on the topic of spherical coordinates, section 14.7. Spherical coordinates are written as ordered triples with rho, phi, and theta. Rho is the distance from the point to the origin, so you can see in this diagram it's going to be the length of this line segment. Phi is the angle that the ray between the origin and the point makes with the positive z-axis. So it's this angle right here between the vertical axis and the line that rho was the length of. One condition is that phi is always between 0 and pi, because that would complete a full positive z-axis to negative z-axis. Theta is the angle from cylindrical coordinates, so you should be familiar with it. It's between 0 and 2 pi being a full circle rotation. So what you would do is project your shape down into the xy plane and figure out your bounds on theta based on that. We have 5 equations relating spherical coordinates to Cartesian and cylindrical coordinates. The first one is that r is equal to rho sine of phi, z is equal to rho cosine of phi, x is equal to r cosine theta, which is cylindrical, which equals in spherical to rho sine phi cosine theta, and y is rho sine phi sine theta. In addition, rho is equal to the square root of x squared plus y squared plus z squared. So you can see it would be easy to express a sphere in spherical coordinates. In addition to spheres, the easiest things to express in spherical coordinates would be cones or planes hinged on the z-axis. So you have spheres, cones, and planes. And I want to show you a couple examples of this. So here in this diagram, we show you a cone, a plane hinged on the z-axis, and a sphere. For the sphere, it has radius a, and our equation would be rho equals a. So rho equals whatever the radius of the sphere is. For the cone, you basically just have a fixed angle. So you would have your angle of whatever the angle with the positive z-axis is. Phi equals that number, and that would be the equation of your cone, where rho and theta vary. Now the plane is given by theta equals some number, where rho and phi vary. So these are the 3 easiest shapes to express in spherical coordinates. Next, I'm going to show you an example of a cone where the equation is phi equals pi over 4. So basically, what I'm saying is that phi, this angle right here, is pi over 4 degrees from the positive, or pi over 4 radians, excuse me, from the positive z-axis. And then, because it's the full circle of the cone, I would have that theta is all the way from 0 to 2 pi. So I get that full circle rotation of the cone. And then rho would vary depending on how far out your cone goes. So as your cone expands further and further out in these directions, your rho would increase. So that equation, phi equals pi over 4, would express that cone. Here's another example where we have 2 shapes that are meeting. So we have a sphere and a cone. The cone is phi equals pi over 3, so that's telling us that the angle from the positive z-axis to the edge of the cone is going to be pi over 3. And then the sphere is rho equals 1, because no matter which way I go out from the origin, I'm going to get a radius of 1. And so we could express the two shapes in this picture using those two equations. Okay, now evaluating a volume using a triple integral in spherical coordinates can be a bit tricky when you're trying to figure out your bounds. If you're given rectangular coordinate equations, you want to use the conversion equations to change them to spherical. Then you want to find your limits on rho as functions of phi and theta. Find your limits for phi in terms of theta or as constants, and find the limits of theta as constants, because you always have to have constants as the outer bound in your integral. So basically, what I would end up with for a volume is I would have my region, and then I would have rho squared sine phi d rho, d phi, d theta. And now the bounds on this outer one are going to come from my theta, the middle one are going to come from phi, and the innermost will come from my rho equations. So that's how I would set up any volume equation. And make sure you have this integrand rho squared sine phi. The next thing that I want to do is walk you through this example where we're actually setting up a triple integral that would give the volume of the region they're asking for. So the region D is bounded below by the plane z equals 0, above by the plane x squared plus y squared plus z squared equals 4, and on the sides by the cylinder x squared plus y squared equals 1. We want to set up a triple integral in spherical coordinates that gives the volume of D. Now the first thing I want to do is figure out what kind of shapes I'm looking at. So I'm going to try to graph this. The x squared plus y squared plus z squared equals 4 is something we're very familiar with. It's going to be a sphere centered at the origin with radius 2. And so in spherical coordinates, this gives me the equation rho equals 2. Now the next equation is a cylinder, x squared plus y squared equals 1. It has radius 1. So if I graph those in 3 dimensions, I have my cylinder with radius 1 and my sphere with radius 2. What I'm looking at is this shaded region that's inside the cylinder and capped on the top by the sphere. So it's this cylinder has a flat base on the z equals 0 xy plane, and it has this spherical cap on the top. Now the next thing I want to do is change my cylinder equation to spherical coordinates. So what I'm going to do is I'm going to substitute my conversion equations in there. And so what I have is I have rho squared sine squared phi cosine squared theta plus rho squared sine squared phi sine squared theta equals 1. So I just substituted in my x and y conversion equations. And now what I'm going to do is factor out the rho squared sine squared phi, since that's in both of them. So I have rho squared sine squared phi, and then what's left is cosine squared theta plus sine squared theta, which I know equals 1. So my final result is rho squared sine squared phi equals 1. That's my equation of the cylinder in spherical coordinates. The next thing I want to do is figure out where the cylinder and the sphere intersect. So find the intersection. That's going to be a circle, as you can see on the graph, and it will be capped on top by the sphere, but our actual intersection will be a circle. So I have my sphere is rho equals 2. My cylinder is rho squared sine squared phi equals 1. So I put them together. So I get 2 squared sine squared phi equals 1. I substituted in rho equals 2. This becomes sine squared phi equals 1/4. So just divide both sides by 4. And I take the square root of both sides. I get sine of phi equals plus or minus 1/2. Now, since phi is restricted to between 0 and pi, we only have the positive 1/2. We'll only have positive sine values, since sine is like the y in our unit circle. So we have sine of phi equals positive 1/2. Now this gives us phi equals pi over 6. And you might wonder, why aren't we using the 5 pi over 6? Well, the reason we don't use it is because that would be the angle down below the xy plane. So we don't use 5 pi over 6 because that would be this angle down here. Okay, now we're ready to start actually building our volume integrals. So there's our intersection, phi equals pi over 6. And here's our graph. What we're going to do is look at the different ranges of phi. So if I look at this cone that has its tip at the origin, what I can see from that is that my phi is going to be between 0 and pi over 6. So it's 0 when it's on the z-axis, and then it gradually makes an angle when it gets to the point of intersection. It's at pi over 6. So I'm going to split apart my region into this cone and into everything else in the cylinder that's not in the cone. With this cone, we know that the outer edge for rho will always be the sphere, and the sphere has a radius of 2. So we're going to have 0 is less than or equal to rho less than or equal to 2, because the bound on the sphere is 2. Now the next thing we want to figure out is theta. So I'm going to have 0 less than or equal to theta less than or equal to 2 pi, since the projection onto the xy plane is a full circle. So this gives me the following integral for the volume of that cone. So I have 0 to 2 pi, 0 to pi over 6, 0 to 2, and then the standard integrand for the volume in spherical, rho squared sine phi d rho d phi d theta. So that takes care of the cone. Now we have to figure out the other part. So this part here is shaded in blue. So if I look at that, I know that for this part right here, phi is varying between pi over 6 and pi over 2. It's at pi over 2 when it's actually on the xy plane, making a 90-degree angle with the positive z-axis. Now, the outer bound for rho is on the cylinder. So what we're going to do for this section is use the equation of the cylinder to find the upper bound for rho. So basically we have the equation rho squared sine squared phi equals 1. That was what we found as the equation of our cylinder. So from there, I'm going to divide both sides by sine squared. So I get rho squared equals 1 over sine squared phi. Take the square root. I know rho is positive, so I don't have to worry about plus or minus the square root. Just take the positive square root. So rho equals 1 over sine phi. So rho equals cosecant of phi. So our bounds for rho become 0 is less than or equal to rho, less than or equal to cosecant phi. Now we're almost done. We just need our theta bounds for this area. Now, basically we have theta between 0 and 2 pi because the projection onto the xy plane is a full circle. So we don't have to worry about cutting it at some point. So putting that all together, I have 0 to 2 pi, pi over 6 to pi over 2, and 0 to cosecant phi, and then my standard integrand for spherical coordinates. And now I just put it all together. We found the volume of the cone and the volume in the cylinder outside of the cone. And so I have the total volume is the sum of those two triple integrals. So hopefully you could see how phi sometimes requires that you break apart the integral into two sections, depending on your outer bound being a sphere or cylinder. And you always look for the easiest way to break it apart. Sometimes if you just have something like a solid sphere, you wouldn't have to break it apart. You could do it with one triple integral. But in this case, it ended up being easier to break it apart.